All right, let's begin. Hello, and welcome to this edition of our global webinar series. Today's topic is designing in the best passive components for resonant converters. My name is Wilmer Compagnoni, and I lead the technical marketing team at KEMET, and I'll be moderating today's webinar. We're very pleased to find that you've found the time to join our webinar, and today's presenter is Atsuko Hoffman, one of our FAEs. With that, I hand this over now to Atsuko. And hello, Atsuko. Thanks for your time today. And please tell us about yourself and begin your webinar.
Thank you, Wilmer. My name is Atsuko Hoffman, and I am a field application engineer based in Milpitas, California office. I have about 20 years of semiconductor and passive component industry experience. I've done some work in component design and QA. I did some product management, and then now I am in technical sales and supporting salespeople. And today's webinar, we're going to cover many stuff. But we're going to go over power conversion top-level schematics first, and we're going into LLC resonant circuit that used in those power conversion, the blocks. And we're going to talk about choosing the right capacitor in those resonant circuit application. And then we're going to go through example how to choose the right capacitor, specifically MLCC. Along with that, we're going to talk about how we utilize our online tool, KCM, and then we're going to touch bases on that a little bit. And then we're going to close with key takeaways and then open to questions. This is a top-level schematic for a three-phase electric vehicle DC first charger that typically charges 50 kilowatts and more. The first stage is an AC to DC converter stage, and that includes the PFC block. The second stage is DC to DC converter stage, and then that includes the LLC resonant converter with integrated transformer that we will discuss about LLC. We will discuss about it in later slides. And the third stage is a secondary rectification stage to deliver the high voltage 400 to 1000 volt to the battery. KEMET work with various EV charging station customers, and we offer different passive components. For the PFC block, we offer three-phase common mode choke coil. We offer safety caps, X and Y caps, also AC harmonic filter film capacitors. And we also offer DC link caps in lyrics, box film, and custom brick film capacitor. We recently started seeing a trend to use MLCCs. MLCCs in DC link application due to adoption of wide-bandgap semiconductor. For the DC to DC block, we offer, sorry, it's not moving. For the DC to DC block, we offer snubber capacitors and resonant capacitors. It's right here. The animation is not working, but oh, here you go. Sorry about that. And then for the last part, the rectification stage, we offer output filter capacitors. It could be the lyrics or the film capacitors. I mentioned about wide bandgap semiconductors, barium nitride and silicon carbide. Wide bandgap semiconductor have started penetrating not only electric vehicle DC fast chargers, but also inverters of electric vehicle and other applications such as solar inverters. Bandgap band gap energy of the wide band gap semiconductor is higher than traditional silicon. And that gives advantage of working at higher frequency, high voltage, and high temperature. And that's what we call the big three of wide band gap. So why should we use wide band gap semiconductor? Because it allows the device to be smaller, require less cooling, and it could be more energy efficient. The higher power conversion efficiency is a big selling point for the wide band gap compared with traditional silicon-based converter. And you can get efficiency gain of 3 to 10% depending on topology. So what does wide band gap mean for capacitor requirement? So a higher frequency means the capacitor needs to be smaller, low ESR, and needs to have high current handling capability, so the high ripple current capability. Higher operation voltage require capacitors to have reliable performance at higher voltage. High junction temperatures mean that capacitor needs to be operating at higher temperature, like 125 degrees C and above. This graph shows required capacitance of the DC link capacitor over frequency range here. And it is for the 10 kilowatt and a 50 kilowatt and 100 kilowatt converter. As the frequency goes up, the required capacitance becomes smaller right here. So at the lower frequencies, like 10 kilohertz to 40 kilohertz, that used in traditional silicon-based semiconductor converters, you need many microfarad capacitance gearing towards to film cap or electrolytic capacitor solutions. As the frequency goes up, let's say above 100 kilohertz, which are more of silicon carbide and then gallium nitride operating frequency range, the capacitance requirement goes down to a few microfarad and less. And the ceramic capacitor become feasible to use those, the frequency range and with the wide band gap semiconductor. And we see the same trend, not only the DC link that we talked here, but also we see that in resonant circuit and in the snubber application as well. We mentioned about polypropylene film capacitor in traditional low frequency converter. The polypropylene film capacitors are usually rated at 105 degrees C or 110 degrees C. As you can see from this graph, operating life becomes a little bit shorter at higher frequency, higher temperature, and the voltage and then the current needs to be derated at higher temperature as well. In regards to high operation frequency, dissipation factor for the polypropylene film cap increases significantly above 100 kilohertz. As you can see, around 100 kilohertz, the dissipation factor goes up right here. So we see polypropylene film cap faces challenges at high temperature and high frequency circuits. Now, as a capacitor manufacturer, we are working to improve performance and characteristics of the film capacitor, but we see more designs utilizing ceramic capacitors in resonant application or film capacitors in parallel with ceramic capacitors in DC link application for wide band gap based converters. We talked about capacitor trend and then wide band gap and versus traditional silicon-based converters. And now we are going to take a look at resonant converter block in this section. Various topologies are available for LLC resonant circuit and resonant converters. And it could be high voltage, it could be low voltage application. It can be used in wide-bandgap semiconductor converters. One of the benefits is 0-volt switching that reduces switching losses drastically. And you can achieve very, very high efficiency. We're talking about 98% efficiency depending on the topology. It can be operate at high frequency, meaning you can use the smaller passive component. Resonant capacitor is used in the circuit, and the requirements are usually, we usually see are low ESR, high ripple current, capacitance stability, and frequency range between 100 kilohertz to 1 megahertz. This table summarizes capacitor requirements for high frequency resonant circuits such as density, capacitance stability over temperature, capacitance stability over voltage, low ESR, and so on. And then we are going to take a look at 4 important requirements, especially for MLCC in next few slides. This is a chart that shows dielectric constant versus temperature. When you talk about MLCC, there are few classes, and one is class 1 dielectric, such as C0G and E2J, and then the second one is class 2, X7R and then X5R. And as you can see in this graph, the class 1 dielectric have very, very stable capacitance, dielectric constant over the temperature range, whereas class 2 dielectric like X7R and X5R, it is stable, but it's not as stable as the class 1 dielectric capacitors. Now let's take a look at stability over voltage. For class 2 dielectric, especially X7R and then X5R, we all know that there is a DC bias effect. So if you put the DC voltage, apply the DC voltage to the capacitor, and then you gradually lose the capacitance. And it is because of it's material dependent. X7R is usually barium titanate based. So because of that material, you will see the DC bias effect, and also the AC bias effect for the class 2 dielectric. But if you take a look at class 1 dielectric MLCCs, you do not see any voltage effect, either DC bias or the AC bias. So it is very stable dielectric. When you look at ESR versus frequency, right here, the class 2 versus class 1, class 1 has very, very low, much lower ESR compared with class 2. And then here, you see some noisy the signal here, but that's because, the class 1 dielectric, especially our calcium zirconate based class 1 dielectric, has very, very low ESR, and it's kind of getting into the range that it's difficult to measure actually ESR. And if you're getting into 1 ohm range, it is very, very difficult to measure. And then because of these low ESR, you see on the graph right-hand side that the ripple current capability of the class 1 C0G or U2J is much higher than X7R class 2 capacitors. So what is the best choice of capacitor technology for high frequency power resonating applications? In this table, we have on the left-hand side, we have required capacitor characteristics in right here. And then we compare different capacitor technology, class 1 dielectric MLCC, polypropylene film MLCC, and then class 2 MLCC. When you look at this matrix, you can see that class 1 dielectric C0G or U2J MLCC can provide most of the desirable capacitor characteristics for the resonating application. We're moving into the next section, and then we will take a look at MLCCs for power resonating application. So historically, MLCC voltage is rated at DC voltage. And it does not mean you cannot use the part in AC application. You can still use it, and many customers do use MLCC in AC application. But DC voltage, rated voltage, does not mean AC rated voltage. So if you have 1000 volt DC part, you cannot use it as 1000 volt AC rated part. So what is the AC voltage rating for an MLCC? Customers ask us this question all the time, and our answer is, well, it all depends. And the customers do not like this answer, but we're trying to help, and we're hoping to explain why it depends, why we say it depends, and what factors influence AC voltage and AC current in ceramic capacitors. So when we talk about AC voltage and AC current rating, there are two considerations in AC to make in AC application. The first one is high AC voltage, or what we call the voltage limited region. That's right here in this plot. The second one is heating due to I²R losses, which is what we call current limited region right here. So this graph is an example plot, and this is available for each part type on our online tool, KCM. You see flat voltage here, right here, and it decreases as the frequency increases. And you will see increased current right here, and it levels off at higher frequency. So you see these two distinct regions, and we will show you what creates these. So when you look at AC characteristics of MLCCs, impedance versus frequency right here, impedance decreases until it hits the resonant frequency of the capacitor, and then it starts increasing again. It's the same for the ESR as well, going down until you hit the resonant frequency. And here is the RLC equivalent circuit schematic, and you can calculate either it's the voltage or current, whichever you want to take a look at. And here you have AC voltage based on AC current right here going through the part. And then you have ESR, ESL, and then the capacitance here. And then, if you have AC current right here, it is based on AC voltage, and it's a function of ESR, ESL, and then the capacitor. Again, there are two distinct regions, voltage limited regions, and then the current limited region. And then we're going to touch base on this current limited region first. So if we're going to calculate AC current based on AC voltage, here is the formula. And then the omega is 2 pi multiplied by frequency here. But the ESL is so small for MLCC, and you can, it's negligible. So you don't have to worry about that. But if you look at this formula, and then if you hold AC voltage very constant, what you see from this formula is that the higher frequency results in higher AC current, and then a higher capacitance results in higher AC current. So you can see that capacitor with higher capacitance value or operating at higher frequency, you are going to get more AC current. So the higher capacitance and frequency, even though the AC voltage is low, you can get a lot of AC current, ripple current. Here are some examples. You have 15 nanofarad MLCC operating at 100 kilohertz, and then the AC voltage is 10 volts RMS, and then you get about 94 amps RMS current. If you use larger capacitance and then at higher frequency, say 150 nanofarad, and then a 1 megahertz, at 1 megahertz, even the AC voltage is the same, 10 volt RMS, you can get a lot more current, 9.4 amp RMS. So what does this mean? If you look at the simple RLC model here, you can calculate the power using I square R, the formula. And then using this power dissipated into the capacitor, you can calculate the temperature rise using the power multiplied by thermal resistance of MLCC. And this is exactly how the calculation works in our simulation tool KSIM. And then we use this calculation to create this plot here. Example, for this part type, CKC, blah, 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 this part type, ESR is 2.55 milliohms, and then it's going through, we're putting 11.4 amps RMS current into the part, and then the arc theta of this part is 59.9 degrees C per watt. You can get this, the thermal resistance value from the plot right here. It shows the arc theta here. And if you do use this and then calculate, you calculate that, you can get power dissipation of 0.33 watt. And then you can calculate the temperature rise in a component as 19.8 degrees C. So this calculation will determine if the part is suitable for an application or not. And we can call this the safe zone temperature, and it helps us to understand the part is operating at acceptable temperature range or not. So here we have kind of summarized the table, but if the temperature zone is less than 25 degrees C above ambient, we call it, it's a low risk operation range. If it is between 25 degrees C and then 50 degrees C, we call it medium risk. It depends on applications. And then if it is above 25 degrees C, if above 50 degrees C, we are increasing at risk of thermal runaway. So the part is getting heat up too much. So we don't recommend to use MLCC in that condition. Now, there are external factors affecting AC current performance. It's not only this I square R losses, but also some other factors such as ambient temperature, thermal characteristic of PCB, above active and passive cooling of the MLCC, and the proximity to the part to other sources of heat. So for example, if you're putting MLCC right next to the high heating, like a switching semiconductor on the same PCB, and then that will affect the ripple current capability of an MLCC. Now, we have seen customers using MLCC at very high power level these days because of the wide band gap semiconductor coming along. And you'll be surprised, designers do not think about the thermal management for the MLCC, how to get the heat out from MLCC, but it is very, very important. It's the same theory as transistor. We know that every designer uses transistors at high power with some type of thermal management. Just like you want to get more power out of a transistor, you want to get more power out of from MLCC, and you have to have some type of thermal management. Either it could be adding heat sink, increasing traces to pull the heat out, or active cooling. Any kind of thermal management helps. And these factors influence MLCC's ripple current, just like the transistor. With this all calculations and measurements, we have developed typical AC current performance plot. And then this is on our data sheet, ripple current versus frequency, and it shows different part type right here. And remember, as I mentioned, this is just a typical plot. So, as you get heat out of MLCC more, you can get more ripple current capability out of an MLCC. And this summarizes the current limited region. Now we're looking into this voltage limited region. As you can see here, at lower frequencies, the voltage is very flat. You cannot use any more voltages. The reason being is because in this region, amount of power dissipated is not high enough to overcome, a few rules we have on maximum voltages that you can use on MLCCs. Now, if you look at voltage calculation based on AC current, here, ESR, ESL, and then J omega C and so on. Now, again, we can neglect the ESL value because it's so small. If you hold AC current stable and a constant, you would see from this equation that lower frequencies result in higher AC voltages, and then a lower capacitance result in higher AC voltages. So even if ripple current does not cause excessive heating, peak AC voltage needs to be considered in this region. Just a quick reminder, the peak voltage is equals to peak voltage divided by 2. So here are some rules. Number 1, peak voltage plus your DC voltage must be less than DC rated voltage of the MLCC. This is basically AC voltage right here, superimposed on a DC voltage. Rule number two, the peak voltage of your AC waveform must be less than DC rated voltage divided by 2. That translates to VRMS needs to be less than DC rated voltage divided by 2 square root of 2. So this assumes no DC voltage. You're looking at the peak voltage here. These are very, very important rules to remember because, customer, like I said, customer ask us all the time, what is the AC voltage rating of the MLCC? And then, at low frequency region, it is very easy because you just have to plug the numbers into the calculation formula. But as you get higher frequency, if you get the I square R losses exceeding that, you really have to think and then look into KSIM and then think about, thermal management of the MLCC. And if you look at class 1, 150 nanofarad, 650 volt DC part, here is the actual ESR versus frequency curve from KSIM. And then here is the current and voltage versus frequency curve. And based on 650 volt rated voltage, you can calculate RMS voltage of 229 volt. And then that's the max voltage that you can use until you get to the current limited region right here. And where the voltage starts to drop because you cannot have more voltage of that part, as now you are limited in terms of amount of current you can put through to MLCC at high frequency range. So we do ripple current measurement at KEMET lab, and what we are trying to characterize is that our part is subject to under high current condition. So we put our part to high current test, and then what we're trying to do is trying to mimic as much as we can to real world AC ripple current environment. Here, what we cannot do is real application like the switching. We don't know how customer uses our MLCC and with what kind of ICs. We don't know that, so we cannot duplicate that. So please note that our waveform is pure sinusoidal waveform and pretty clean. When you get into high frequency switching components, you will see waveform that are not completely sinusoidal. So, we always tell customers we can provide our typical ripple current plots for MLCCs. And we always recommend customers to put our parts on their board and then a test to verify. And then, how we do ripple current measurement, we have a YouTube video. It's about 7 minutes video, and it's pretty easy to understand. So if you have a chance, please take a look at it. Okay, now my screen is not working well. I'm sorry. Okay. So the ripple current measurement plot look at temperature difference between top of the part and then one of the termination. And that helps us to understand how easy the part can have that, how easy the part can have heat removed from it. You can also see here in blue line here, the measurement result for temperature difference between the top of the part and then the ambient temperature. And then, the closer these are together, easier to pull the heat out. And that concludes the voltage region and then current limited region and so on. And then we're going into example here. So in resonating circuit, we need more power. So most of the customers we see, they use the same series and then a parallel connection of the capacitor bank. And then here you can see, we have a single MLCC, 100 nanofarad, and then 1000 volt and 10 amp RMS current. And then if you connect that two in series, as you can see, you can get rated voltage of 2000 volt. And then if you put the string in parallel, then you can get twice as much as AC current, 20 amp RMS, while you're maintaining the capacitance the same, 100 nanofarad. And then if you do the same for the 3 in series, connect capacitor 3 in series, then you have 3000 volt. And then you connect 3 strings in parallel, then you will get 30 amps RMS. So there are many different combinations that you can achieve, your target for the resonant capacitors. Here we have some example, actual example. This is a 16 by 4 array. The total capacitance of 880 nanofarad, and then the current capability of 240 amps at 200 kilohertz. But if you can look at, if you take a look at the left-hand side picture, it's pretty big. But we offer some solution, what we call the Connect technology, and it's a leadless stack technology. And you can get the same capacitance and then the same ripple current capability by using Connect technology. But as you can see, it's a 4 by 4 matrix, and you can save a lot of space. So, you know, if you don't have space, we have some solution. Here is actual example. We have LLC resonant converter, and total capacitance required is 100 nanofarad, and AC voltage 90 volt RMS, AC current 22.6 amp RMS, and then operating frequency at 400 kilohertz. So the first thing to choose the capacitor, you have to determine, you know, the required voltage. You know, what will be the required voltage rating for the capacitors, and then you can check. You can calculate using this formula. For this case, we need at least 254 volt DC rated part. So if you take a look at our KC-Link data sheet waterfall table, you see two possibilities. One is, let's see, I'm trying to get laser pointer right here. Okay. So we have two solutions. Both are 100 nanofarad and then a 500 volt rated DC voltage right here. So we are okay with capacitance target and then the rated voltage target. But what about ripple current capability? Are they good? So what you need to do is that you have to go to KSIM, our tool KSIM, and then you go to the current voltage versus frequency plot. And then you can see for each part, you know, at certain frequency, in this case, at 400 kilohertz, you know, what would be, you know, what's the ripple current capability of this part. So for the first part, it is 16 amp RMS right here. So it will not work because it does not meet the target ripple current value here. And then for the second part, you know, you do the same, and then it turns out it's 11 amps RMS. So it's less than what you target. So these two solutions will not work well. So these two will not work. So what can you do? What about you are putting, if you put on two capacitors in parallel like this? So you maintain the same rating voltage, but you can increase the ripple current rating in that way. So here, you know, going back to the data sheet again, and then we have 47 nanofarad 500 volt rated part. And you can get the ripple current capability of this part at 400 kilohertz from the data sheet here. Or if you want to get exact number, you can go to our KSIM, and it turns out to be, you know, 11.5 amp RMS at 400 kilohertz. So you're using two 47 nanofarad part in parallel here. So the total capacitance is 94 nanofarad, and voltage rating is 500 volts. So it's good. If you're using two capacitors, you know, the ripple current will double. So the total ripple current capability is 23 amp RMS here. So, you know, I guess, you know, it works very well unless you're targeting the capacitance really close to 100 nanofarad. 94 might be too far. It might work, it might not work. So you can take a look at another solution, maybe. What if we use 3 capacitors in parallel like this? We have 33 nanofarad, 500 volt part. If you take a look at KEMET data, the ripple current capability of this part is 7.4 amp at 400 kilohertz. You're using 33 nanofarad capacitor in parallel, so you get total capacitance of 99 nanofarad, and it is much closer to your target 100 nanofarad. And voltage is of the part is 500 volt DC, so it's good. AC current 22.2 amps. It's a little bit shy from the target value, but it probably works. So it depends, how you decide. So this solution would work. So you can put these 3 discretely like this, or if you don't have the board space, you can put in one connect format, and then you can save a lot of the space on the board. And we talk about a lot of things in this presentation, but as a summary, here are 2 takeaways for the resonant circuit. We think that the class 1 C0G is the best capacitor choice for those type of application because class 1 dielectric MLCC has capacitance stability versus temperature, low ESR, DC, and then AC voltage, high DC and AC, and then a high ripple current capability, and it can be operated at a very high frequency as well. And then number 2 key takeaway, consideration for MLCC in AC applications. Remember, there are 2 distinct regions, AC voltage for voltage limited region, and the I2R losses for current limited region. And then for those AC applications using MLCC, the thermal management is very important. The more you can take the heat out from the MLCC, you can get more ripple current out of it. So it's important. And then there are series and then parallel connections to meet your voltage capacitance and then ripple current target. And you can determine the right capacitors using our data sheet and then the KEMET tool. And that concludes my presentation. Wilmar, I'll get back to you.
All right. Well, thank you, Atsuko, and thank you, everyone. I think that was informative. That was quite a bit of things. We definitely went a bit over time. So I'll open it up, obviously, to some questions now, anything that might come in. And so we'll give a little bit of time for anybody that might have a question to submit those through the Q&A portion of the Zoom window. While perhaps some of those questions come in, Atsuko, I do have one of my own. You mentioned earlier that in some occasions in DC link applications, we see that ceramic capacitors are used in parallel with some film capacitors. Can you give us some insight as to why that might be?
So the DC link capacitor is just, the filtering the ripple voltages at DC section, right? And the film capacitor works well at lower frequencies. So people use, some of our customers use that film capacitors to filter the lower frequency portion of the noise. And when you use the wide-bandgap semiconductor, the frequency might be a little bit higher. So, and then many customers use those MLCC in parallel with film cap to filter the higher frequency portion of the noise. So the lower frequency film cap for lower frequency, and then a higher frequency MLCC for higher frequency.
Okay, I see. So the ceramic capacitor is just filtering some of those higher frequencies.
Yes.
Right. We had a question to submit the link for that YouTube video about the 50 amps through an MLCC. I posted that in the Zoom chat, and we'll also post that in the follow-up email and things like that. So with that, I know we're a little bit over time. I thank everybody for staying on an additional 15 minutes, and thank you very much, Atsuko, for putting all this material together for us. So thank you for that, and we look forward to seeing you at another one of our global webinar series. So thank you, everyone.
Thank you.